Hello, everybody. I hope and trust that you had an amazing week so far and that you had an amazing weekend. I'm just, replicating one of my favorite speakers and his introduction when he does his videos. And yes, we meet again. And last week, we looked at IP addressing. We covered what is an IP address. We looked at the number of bits that an IP address has. We went ahead and looked at different classes of IP addressing. We converted our IP addresses from binary to decimal and decimal to binary. We went and further looked at the classful versus classless boundaries, just trying to understand what the difference is. And today we're going to be looking at subnetting. I remember last week we had to wrap up without touching much of subnetting. So today we're going to be starting with subnetting and we're going to go into detail. We're then going to look at IPv6. We are also going to look at DHCP DNS on the network services. We are going to look at our data center architecture and look at the different architectures that we can implement in our data centers and in our networks. And then we should close by looking at cloud concepts. So it's a very packed lesson, and I'm really looking forward to looking at all those topics and being able to go into detail. So I'm just going to share my screen and then we can start off. All right, so here we go. The last time I mentioned that when you're subnetting, I want you to think of a box of pizza and you needing to share it amongst different people. I remember last week in the last lesson, I mentioned that when you buy a pizza, and you need to share it amongst 4 people, you are going to cut it into 4 slices so that everyone else has got an equal share. And if there are 8 of you, you are likely going to cut it into 8 slices so that everyone else has an equal share. And the other example that we basically spoke about was, land. When you buy a stand to build a house, most developers buy a huge piece of land, and what they then do is that they subdivide that land into smaller chunks. So they'll buy this piece of land as one unit, and then they'll go ahead and then subdivide it into smaller stands, and then they sell those stands at a price. And the reason why they subdivide it is because when it's one chunk of land, it's probably not going to be useful to one family because it's too big a piece of land. But when they break it down into smaller stands, it means that they're able to put more houses and create neighborhoods. So the process of subnetting, when you think of subnetting, it's basically breaking down something that is bigger and making it into smaller chunks. So in our case, these stands would be minor or tiny subnets of the bigger piece of land. This is equally true with our pizza. Our pizza is like this. We cut it into 4 slices. Each slice becomes a subnet, if you want to call it in networking terms. So when we're talking about subnetting in networking, all we are doing is breaking down a bigger network into smaller segments. And why would you do that? Sometimes you go to, remember we spoke about the fact that there are routable IP addresses which can talk on the internet, and then there are private IP addresses which are not routable on the internet. So in order for you to go online, you need to get a public IP address. So most of the times you go to your internet service provider and then you ask them for a block of IP addresses that can allow you to then take you to the internet. They might give you something like this, 105.20.0.0/24. So they'll give you a /24 block, which has about 254 hosts. And then you will then subnet this into smaller chunks in order to cater for different needs for your organization. So in this case, we're looking at subnetting in the context of the internet, but we don't necessarily subnet just because you want to go online. Sometimes internal to your organization, you have different departments. You might want to create a network for your server infrastructure. You might also want to create a network for your desktop users. And you might want to create a network for different departments, right? So you've got different departments. And all this needs to be segmented into unique IP addresses so that you can be able to then apply security boundaries between these respective subnets. And in order for you to do that, most organizations will have a block of IP addresses, which probably are 10.0.0.0/8. And then they will then subnet that 10.0/8 and maybe go with 10.0.0.0/16. That becomes your server subnet. And then 10.1.0.0/16 becomes your desktop subnet. And then 10.2.0.0/16 becomes your department. So we subnet for multiple reasons. And we are going to look at what are the requirements and how do we get to subnet devices on our network. And to kick off, there are 5 questions that we need to answer when we want to subnet our network. And the first question is, how many subnets do you want from the chosen mask, right? So when I'm saying how many subnets, you need to ask yourself, how many networks do you want to create? Do you want to break it into 4 networks? Do you want to break it into 8 networks? And in each network, how many devices do you want in that particular subnet? Because all that is going to determine the size of your network, and it's also going to determine how many hosts can be supported on the network. The second question is, how many valid hosts do you need per subnet, right? How many end users are going to be connected to that subnet? Do you want to connect 16 devices? Do you want to connect 32 devices? Do you want to connect 500 devices? Based on these, the answer to these questions, your subnet is either going to go bigger or smaller as you provide an answer to these questions. The next one is, what will be the valid subnet? The fourth one is, what will be the broadcast address for each subnet? And then the last one is, what are the valid hosts for this particular subnet? And I'm sure by now you're wondering, okay, I'm a bit clueless, where are we going with this? So we're going to look at an example and we're going to break it down. I remember the last time I mentioned that there's a formula that we use when we are subnetting, right? Because when you subnet, you are creating smaller networks out of a big network that has been provided. And in order for you to do that, we have to use something known as borrowing of bits. And what do I mean by borrowing of bits? So let's take an example. We have a network 192.168.0.0/24. And then your manager comes to you and he says, can you please break this network into 4 subnets? Right, because we've got a project that needs 4 different networks for whatever the project wants to achieve. So how do we go about, then solving this particular problem? Now, the /24 notation means that our subnet mask is 255.255.255.0. So we are drawing the line on this particular part. So out of 24, we say that our IP address is 32 bits, which leaves this last part being 8 bits. So when we are subnetting, we are going to be borrowing bits in that last octet, depending on the size of the subnet that we want to create. So what's the mathematics behind it? We said the formula for the number of networks is 2 to the power x, where x is the number of borrowed bits. And what does that mean? So remember, our request is to create 4 networks. So we need to ask ourselves, to what power of 2 do we need to raise it in order for us to get 4? And I remember the last time I mentioned that our networks start with 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 5, 6, and 2 to the power 7. And we say the equivalent was 1, 2, 4, 8, 16, 32, 64, and 128. So in order for us to have 4 networks, we have this number 4. Now, what is the number that we have raised 2 to the power of in order for us to get 4? And that is 2 to the power 2. So in that case, we are borrowing 2 bits. So if we have borrowed 2 bits, it means that the remaining bits that are unborrowed, remember we are borrowing from this number 8. So if we borrow 2 bits out of 8, it means 6 bits are the unborrowed bits. Right, so if this 6 bits are the unborrowed bits, 2 are the borrowed bits, 2 plus 24 gives us 26. So our subnet increases from a /24 to a /26. I hope that is clear. If not, I'll come again. Right, so we said that our formula of the number of networks is 2 to the power x, where x is the number of what? Borrowed bits. And we said if we are dealing with a /24, it means that the first 24 bits of that IP address are reserved, and we have the remaining 8 bits. And from those 8 bits, we're going to borrow bits in order for us to subnet our network. And I alluded that if we need 4 networks, we'll probably need to borrow 2 bits. But let us look at the example on the screen. So in our example, the 4th octet is 111.000.00. And the number of ones or borrowed bits is 3. So x is equals to 3. And if x is equals to 3, 2 to the power 3 is equals to 8. Which means that if we borrow 3 bits, we create 8 networks. If we borrow 2 bits, we create 4 networks or 4 subnets. If we borrow 1 bit, we create 2 networks. And if we borrow 4 bits, we create 2 to the power 4 will give us 16. So we create 16 networks. So the number of networks that we create is either going to increase or decrease based on the number of bits that we have borrowed. And for every bit that we borrow, we are going to represent it with a 1, right? So the borrowed bits will be represented with a 1, and the unborrowed bits are going to be represented with a 0. And this is a very important part to understand, because the whole concept of subnetting is basically anchored on what I've just mentioned, right? The bits that we borrow become 1s, the bits that we don't borrow become 0s. So if we borrowed 3 bits, it means that of the last 8 bits, remember there were 1, 2, 3, 4, 5, 6, 7, 8 zeros. But now we have borrowed 3 bits, so this becomes a 1, this becomes a 1, this becomes a 1, and then we still have the number of zeros. And before this, we had 24 bits or 24 ones. So 24 plus 3 makes this a slash 27. And we're going to look at examples that are going to help us break this down and make sure that we've got very good clarity. And if I lose you somewhere along the lines, just let me know in the comment section, and I can be able to come back and just clarify, because this is important. So we said the number of networks is going to be in relation to the number of bits that you're going to borrow. The less bits you borrow, the less the number of networks. The more the bits you borrow, the more the number of networks. Okay, so we have dealt with the networks part. Now let us look at the number of hosts that you can have per subnet. And the formula is okay. The formula for the number of hosts per subnet is 2 to the power y minus 2, where y is the number of unborrowed bits or the number of zeros. So earlier on, we borrowed the first 3 bits in the octet, and we had 5 unborrowed bits. So the number of hosts on a subnet becomes 2 to the power 5 minus 2. And 2 to the power 5, 2 to the power 5 is 32. 32 minus 2 gives us 30 hosts. And why are we separating by 2? It's because there are 2 addresses on the network that we can't utilize. The first one is what is known as the network address, and the second one is what is known as the broadcast address. These 2 addresses are reserved on any subnet that we run on a network. So we are separating by 2 because of the 2 IP addresses that we can't utilize. So now we have realized that if we borrow 3 bits, we are going to create 8 networks. And each network is going to have 30 hosts. So the number of networks or the number of subnets is going to be in relation to what it is that you want to achieve. How many networks do you need, and how many hosts per network do you require? And that is going to then become the determining factor as to how you're going to subnet your particular network. So now we know the number of networks that we have. We know the number of hosts that we can have per network. The third question that we need to answer is what are the valid hosts per network. And how we calculate the valid hosts per network is using a formula where we separate our subnet mask from 256. And what do I mean our subnet mask from 256? Remember the last time we said our IP address is made out of 32 bits. And we said these 32 bits are broken down into 4 octets. And we said when we're converting our IP address between binary and decimal, we use the binary value 128, 64, 32, 8, 4, 2, 1. And our IP address is a combination of ones and zeros converted from decimal into binary. And if we were to convert this binary address into decimal, we're adding 128 plus 32, which gives us 160, plus 1, it means 161, right? I'm just refreshing our memory so that we are on the same page. So now, earlier on, we borrowed 3 bits, right? The first 3 bits of the last octet. We borrowed the first 3 bits, which means that our binary equivalent is going to be 1110000. Sorry, 5 zeros. 8, 4. Okay, this I missed 16 here. Okay, so 5 zeros. So 128 plus 64 gives us 192. 192 plus 32 gives us 224. So our subnet mask is a 224. Remember earlier on we covered, let me just see if I can get to that table. I remember I mentioned that we need to master, and get to that exactly, this table. I mentioned that we need to master this table because we are going to need it as we progress in our IP addressing lessons and as we look at subnetting. And I said, as you increment, right? So let's start with the /24. And with the /24, we say that the first 24 bits are reserved for the network address. The last 8 bits are reserved for the host address. And then a /25 means that we have borrowed 1 bit from the host portion of the network address, and we've added it onto the network portion of the address. So that becomes a /25. A /26 means that we borrowed 2 bits. A /27, we borrowed 3 bits. And a /28, we borrowed 4 bits. And as you notice that as the value increases, the number of hosts per network is decreasing. So on a normal /24, we have 254 hosts on that particular network. On a /25, we have 128 hosts. On a /26, we have 64 hosts per network. On a /27, we've got 32 minus 2, which is 30 hosts per network. On a /28, you've got 16 minus 2, which is 14. So this table is very crucial in you being able to subnet in your mind, because you know that the more I borrow bits going to the right-hand side, meaning as I borrow more bits from the host portion of the network address, my networks are increasing, but my hosts per network are decreasing. All right, so I've basically just reiterated this particular table. We can go back to our slide. Just a second. Okay, so back on our slide. So we said our subnet mask is 224, and 256 minus 24 is equals to 32. So our networks are increasing in 32s, meaning the first network is a 0, the second network will be a 32, the third network will be a 64, the fourth one will be 96, the fifth one will be 128, 160, 192, 224. So our networks are increasing in 32s. So that's the first part. So our valid subnets, if we're writing our IP address, so 192.168.0.0/27 would be our first network. Our second one would be 192.168.0.32/27. Our third network is going to be 192.168.0.64/27. So these are three different networks, all being 192.168.0/27 subnets. So we have answered the valid subnets. Now we need to know what are the valid hosts in each particular subnet. And our valid hosts would be the fourth part is the broadcast address, right? The broadcast address is the number before the next subnet. So our first network was 0 ending on 32, and the number before 32 is 31. So that then becomes our broadcast address. On the 32 network, our broadcast address is 63. On the 64 network, our broadcast address is 95. On the 96 network, our broadcast address is 127, and that basically goes on until you get to 255, being your last broadcast address. And the number of valid hosts per network is going to be the values between our network address and the broadcast address, and that will be 1 up to 30. That becomes the valid range. And then on the second subnet is going to be 33 all the way to 62, being the valid hosts in that particular subnet. So we're going to look at an example, and we're going to put all these steps into practice, and we're going to see an outcome that will then help us reinforce and understand IP addressing, subnetting. All right, so let's. All right, so we're going to look at this example. I hope it's clear on the screen. So in our example, we are going to be borrowing 1 bit, right? We're going to be borrowing 1 bit, and we want to see how many networks we can create, and we want to see how many hosts we can have on that particular network. And on an IP address of 192, just write that down, 192.168.10.0/24. So the first 24 bits have been reserved for the network ID, and then the last 8 are for the host ID. And we're going to be borrowing 1 bit off the last octet. So our first question is 2 to the power x, where x is the number of borrowed bits. And in our case, we're borrowing 1 bit. So 2 to the power 1 is equals to 2. So when we borrow 1 bit, we create 2 networks or 2 subnets. And what are the number of hosts that we have on that subnet? And the formula is 2 to the power y minus 2, where y is the number of unborrowed bits. If we borrowed 1 bit out of 8, 7 bits are unborrowed. 2 to the power 7 is 128 minus 2, 126. So we can have 126 hosts per subnet. And what is our broadcast address? Oh, sorry. What are the valid subnets? And we said the valid subnets, we convert this borrowed bit into hexadecimal or into hexadecimal, and then we separate that from 256. And we said 128, 64, 32, 16, 8, 4, 2, 1. When we borrow 1 bit, it means that we are taking 128. 256 minus 128 is going to give us 128. So our networks are going to increment in 128. So the first network is going to be 0, and the second network is going to be 128. Right, so we can only have 2 networks. We spoke about that here. And each network is going to have 126 hosts. So the valid subnets are 0 and 128. And the fourth question is, what is the broadcast address? And we say the broadcast address is the number before the next subnet. And in our case, 127 is the number before the next subnet. So our broadcast address is going to be 127. And the valid hosts per subnet is going to be the values between 0 and 127. And that is going to be 1 all the way up to 126. So what does that mean? What that basically means is if we have a router sitting on our network, we can divide this network into 2 parts. The first part is going to be 192.168.10.0 all the way up to 127. And the second part is going to be 192.168.10.128 all the way up to 255. So that's how we then create 2 networks, each with 126 hosts per network. So we've looked at one example. We're going to look at another example just to make sure that we're able to reinforce the concept and everyone is comfortable. So in this case, we're going to borrow 2 bits. Why do I say we're going to borrow 2 bits? Because it's going to be a /26. So the /26 has a correlation to the number of bits that we're borrowing. Because remember, the original is a /24. And depending on what we want to subnet, we are borrowing out of the last octet. And each octet has 8 bits. And I'll keep on reinforcing that because that's the crucial information when you're dealing with subnetting. So out of the 8 bits, when we borrow 2, we add them to the 24 to get to 26. And the unborrowed bits become 6, which means 26 plus 6 gives us 32 because our IP address is always 32 bits. So that is very important, crucial to be able to understand. So now let's go through our 5 steps. The first one, 2 to the power 2 is equals to 4. So this will have 4 subnets. And how many hosts can we have per network? Unborrowed bits is 6. So 2 to the power 6 minus 2 is equals to 64 minus 2, which is equals to 62. So we can have 62 hosts per subnet. What are the valid subnets? once again, convert that 128, 64, 32, 16, 8, 4, 2, 1. We borrowed 2 bits, 1, 1, 0, 0, 0, 0, 0, 0. 128 plus 64 gives you 192. And the formula says 256 minus 192 is equals to 464. So our networks are going to increment in 64s. So the first network is going to be 0, 64, 128, 192. And those are the 4 networks that you're going to have. What are the valid hosts? Oh, sorry, what is the broadcast address for each network? It's going to be the value before the next subnet. So the first one is 0, 64, 128, 192. Right, those are the 4 networks. The value before the next one is 63. So for the first network, the broadcast address is 63. For the second network, it's 127. For the third, it's 191. And the valid hosts that we're going to find with that network is going to be the number between 0 and 63. And that's going to be 1 up to 62. So if we were to then subdivide our network and break it down into 4 parts, if you're then going to create a network diagram, it's going to look something like this. The first network is 192.168.10.0, 10.64, 10.128, 10.192. That's how our networks are going to increase. And that's how we subnet our networks in order for us to break them down into ways that are more meaningful in our organizations. And we can then make the networks much more smaller and bigger depending on what we want to achieve. So the most important part that you need to remember when you're dealing with subnetting is the concept that the size of the network is going to be determined by what it is that you want to achieve, right? We're going to look at one last example, and this is common when you got routers on a network that are connecting over what we call a point-to-point link. This is where you're connecting to your ISP, and only 2 IP addresses are being used, right? The one on your side of the network and what's on the ISP side. And in this case, we want a network that can support only 2 hosts so that we don't waste IP addresses. So the question that we need to ask ourselves is, in order for us to have 2 hosts per network, to what value do we need Y to be, right? And for us to have 2 networks, we need Y to be equals to 2, because 2 to the power Y minus 2 is equals to, when Y is equals to 2, 2 to the power 2 minus 2 is equals to 4, 4 minus 2 is equals to 2 hosts. So when we have what we call a /30 subnet, that allows us to have 2 hosts per network. And if 2 bits are the ones that are unborrowed, it means that we have borrowed 6 bits to make 8. So 2 to the power x, where x is equals to 6, would be 2 to the power 6. So that would mean that we're going to create 64 networks, and each network will have 2 hosts. All right. Okay, so that brings us to the end of subnetting. And now we're going to be looking at network address translation. I remember the last time, and I mentioned that when we're going onto the internet, we've got private and public IP addresses. Private IP addresses are not routable on the internet. We looked at the 3 private IP addresses, which is 10.0.0.0/8. We looked at 172.16.0.0/16 and 192.168. And we said those are private IP addresses. When we're going onto the internet, we need public IP addresses. And I demonstrated that the last time by showing you my home network. And I'll just try and have a look one more time, just pull that out. And I said, let me just see if I can zoom that up. Right, and I said when I do a trace going online, I go to my default gateway, which has a 192.168.0 IP address. And then after that, I am taken to my ISP and the IP address changes to 49.192.48.1. And if I stop there, the 49.192.48.1 is a public IP address, which is taking me to the internet. And that basically brings us to the subject of NAT. And NAT is network address translation. All right. NAT is network address translation. And the best example that we can look at when we are looking at NAT is your driver's license and your passport. When you stay within the confines of your country, you can carry your driver's license as your form of identity. If you get stopped, you're able to produce your driver's license, and that is sufficient enough. However, if you want to leave the country, you can't use your driver's license. You need another document, and that document that is universal across multiple countries is known as a passport. A passport is what's going to take you on to the outside world. And that is similar with NAT. Our private IP addresses can't take us online, so we need something that translates our private IP address onto a public IP address. And there are 3 forms of network address translation. The first one is known as static NAT or one-to-one. So when you talk about static NAT, also known as SNAT, right? So S stands for static. This is basically a one-to-one mapping. And what do I mean by one-to-one mapping? It means that for every private IP address that needs to go to the internet, you need one public IP address. So if you've got 200 computers that need to talk to the internet, you're going to need 200 public IP addresses. Now, this is not practical because we don't have so many IP addresses to be able to issue out to everyone. Remember, the whole concept of private IP addresses was trying to solve this particular issue. So what kind of devices use static NAT? They are devices on our networks that we need static IP addresses so that they can be reachable from the outside world. So a typical case in point is your website. It will need to be reached on the same address, or your email server will need to be reached on the same IP address. In that case, you can allocate a static NAT, which means that it's a one-to-one mapping, the private to the public IP address. The second type of NAT is known as dynamic NAT, And with dynamic net, you have a pool of IP addresses. So you'll have a pool, and in this pool, there'll be 10 IP addresses. And these IP addresses can take you online. So depending on who wants to go online, you go, and when you get translated, one IP address out of this pool is going to be used, and then 9 are going to be remaining. When all of the IP addresses in the pool are used, it means that no one can go onto the internet until the ones that are connected have returned these addresses that they've leased for the purposes of connecting to the internet. So that's your dynamic net. And the last one, and this is the most common one, it is known as PAT, or port address translation. And the reason why this is common is because you can use one IP address to take you to the internet. It doesn't matter how many devices are sitting behind that IP address. And most organizations use PAT. And PAT is the reason why we have not run out of IPv4 addresses, because organizations with 500 users in the back can use one IP address to take them to the internet, and that IP address would basically be sufficient. So how does PAT achieve the task of taking 500 users onto the internet? And PAT uses something known as port address translation. So when you go out, so let's take computer A. It is trying to go to this IP address or to this website. And because we are using PAT, the inside IP address, which is the private IP address, is going to be 192.168.10.32. The public IP address, which is known as the outside address, is going to be 13.62.25.100. So computer A is going to be tracked using the port number. So the router that is doing the net translation is going to then track the session and say, okay, fine, I've received a packet from computer A, and I'm going to track it using a local port number of 1034, and it is going to a destination of 2023. And the router then puts that information in the NAT table, so that when the return packet comes back with the port of 2023, when the router looks at its NAT table, it's going to find a match and is going to send that packet back to computer A. On computer B, it is going to track that information using a totally different port number, and that's how it is able to have the translations tracked. So the three types of NAT: static NAT, one-to-one mapping. For every public IP address, you need for every private IP address, you need a public IP address. It is not scalable for end users. It is reserved for server infrastructure. So your email server, that would require a public static IP address. Your VPN server, that's going to require a static private IP address. The dynamic NAT is when you have a pool of IP addresses and you use the pool as required. When you're done, you return the IP address into the pool. And the last one is port address translation, which is a one-to-many, which allows multiple devices to go onto the internet using one particular IP address. All right, so we are now getting to the tail end of our IP addressing, and we're going to be looking at IPv6. I mentioned the last time that IP version 4 IP addresses were at risk of running out. And I mentioned that the reason why we haven't run out of IP addresses is because of port address translation, which allows multiple devices to go to the internet. hiding behind one particular IP address. But we can't sustain this on a longer run. The reason being that there's some applications that don't do well with port address translation. They need more visible IP addresses rather than ones that are hidden behind one particular IP address. So the masters of the internet came up with IP version 6, and this will solve our limitations that we had on IPv4. And an IPv4 address, remember the last time we said an IPv4 address is 32 bits. An IP version 6 address is 128 bits. And to calculate the number of hosts that you can have is 2 to the power 32, which gives you about 4 billion IP addresses on IPv4. On IPv6, it would be 2 to the power 128. And I can't pronounce the number that basically comes up. So there's an excess number of IP addresses. Now, if you look at an IPv6 address, clearly it is way different to an IPv4 and difficult to be able to read or write. So there are certain rules about IPv6 addresses that we need to cover to help us shorten the address and make it more easier to write and not much to configure, mainly to represent it as we write it. And one of the first rules is the leading zeros in an IPv6 address can be ignored. And what does it mean, the leading zeros? The IPv6 address is broken into so you've got 1. So this is an IPv6 address. So when we say that we can ignore the leading zeros, it means that this 0 can be ignored. This can be represented by a double colon. So we can ignore all these, and we can rewrite our address as 2001-0db8 ... and the ... is basically accounting for all these zeros. So that's one way of writing our IPv6 address. So continuous fields containing all zeros can be represented with a double colon, but this can only be done once. And I'm just going to clear my screen. And what do I mean? So let's write a new IPv6 address. So 2001-0db7 0000:0000, and then ADB8 0000:7347. So earlier on, we said that these leading zeros, we could cancel them out and represent them with a double colon. And this statement is saying that this can only be done once. And what that basically means is that on the second address, we can combine these zeros and represent them with a double colon. However, we can't do the same thing on these 2 zeros because there will be no way of the shortened version to represent the IP address in a more accurate manner. So if you are replacing the leading zeros, you can only do it once in any one IPv6 address. So that's the first part about IPv6 addresses. In Network Plus, there isn't much that is covered in IPv6, but you need to understand the number of bits that you find in IPv6. You need to understand how you can represent an IPv6 address in a shortened format. And you also need to know the different types of IPv6 addresses. And the three most common are the routable IP address, which is the equivalent of a public IP address in IP version 4. And this address starts with any number between 2000 and, just take this back, any number between 2000 and 399. So an IPv6 address that starts with 2000, 2001, 2002, 3000, anything between these values as the first 16 bits, that would be a global routable address. IPv4 equivalent is anything that's not a 10.0.0.0/8 or 172.16.0.0/16 or 192, meaning an 8.8.8.8 address is public, but the first 8 is basically the determining factor. As long as it doesn't start with 10, doesn't start with 172.16, 192, then it will be a public address. So something similar with IPv6. They also have what is known as a link local address. And this is what you use to assign to an interface. So if you've got a computer and that computer is on a network running IPv6, you give this computer an IP address, that will be a link local address. That is the IP address of the device. And that starts with an FE80. So when you see an IP address that starts with FE80, it means that that is reserved to a link local, which is more like a private IPv6 address. And then the last one is a multicast address, which starts with FF. So this basically helps you that the moment you see an IP address, IPv6 address, look at the first 16 bits of that IP address. If it starts with the 2000 to 399, that's going to be a publicly routable address. If it starts with an FE80, it means it's a local address, and anything starting with an FF is going to represent a multicast address. And that's all that you need to know when you're dealing with IP addressing in Network Plus. Then these three, two of them we covered in IPv4. So we spoke about the unicast address, and we said the unicast address is the one-to-one address, right? One host talking to another host, that is unicast. Uni being single, multicast is a one-to-many, and we spoke about video streaming services being multicast systems, where if you want to watch the stream, you join onto it, but the source of the feed is one, but the number of devices that are watching that feed are many. And then the one that is in IPv6 that is not in IPv4 is something known as anycast. And anycast is basically one to the nearest. And when I mean one to the nearest, you have multiple devices on a network that share the same address. So I'll try and use something that we know. Right, so let's see. Okay, so let's take this as Netflix. This is the Netflix cloud. And with the Netflix cloud, they've got these routers that are sitting on the edge of this cloud. And these routers share the same IP address. So you're using the same IP address. And depending on where we are located, right? I'm sitting in Australia. So when I connect to watch a movie, I am going to be serviced by the router that is closest to me. That's the one that's going to take me onto the Netflix cloud, which is going to take me to the servers that host the Netflix content. When you connect from the UK, instead of you being brought to this router, you're going to be connected to the router that is closest to the UK. But the address that this router and this router share are the same address. It's just that you get serviced by the router that is closest to you. So that's how Anycast basically functions, right? So one IP address assigned to multiple devices, and depending on where you connect from, you get serviced by the device that is basically closest to you. And I think that basically, wraps up the IPv4, sorry, IPv6. So there isn't much that is covered in IPv6, just understanding that the IPv6 address is 128 bits, and how to easily identify IPv6 addresses, and also how to write an IPv6 address in shorthand. I think later on we're probably gonna go through a series of questions on IPv6. Not the most simplest of protocols of IP addresses to easily master, but with a lot of practice, it is much more easier. There are organizations that are implementing and using IPv6 as we speak, so it's being adopted quite rapidly as it is used in the industry. So the next topic that we're going to be talking about is ports and protocols. Now, this is one of those topics that you need to cram, for lack of a better word. You need to know the protocol and the port numbers. There is no easy way to mastering it. It's just a matter of practice or reading, but there are common protocols that we use on a day-to-day basis when we work on the network or as traffic flows through the network. And some of the most common protocols are DHCP, DNS, FTP, FTP being file transfer protocol. It is used mainly for transferring files. DNS, we're going to talk about it later, which is domain naming system. HTTP, that is the protocol that takes us to, I was going to say the internet, but it's the protocol that allows us to view web pages on servers and on the internet. So it is the most common protocol that you and I use on a day-to-day basis whenever we go online. So whenever you open a web browser, 90% of the times you're going to be running either port 80 or port 443, likely 443 because it is more secure. You've got NTP, POP3, RDP. So there are quite a number of protocols. So I'm just going to run through what the protocol does and the port number that the protocol uses. So what is a port number? A port number is just basically an identifier that identifies traffic as it's flowing through the network. So the challenge that we have on a network is that you've got a pipe, right? So this is your network cable, and these are packets that are flowing through, going to their destination. Now, of these packets, we spoke about the last time that we've got something known as a header, right? And say the header is the information that helps us in routing this packet and helping it to get to the destination. And in the header, we say that we get information about the contents of the packet. And one of the values was the port ID. So the port ID just basically says this packet is port 23, which means that it is telnet traffic. If it's port 443, it means it's HTTPS traffic. So a port number basically identifies a particular protocol as it traverses through the network. So DHCP is dynamic host configuration protocol. This is a protocol that allows us to allocate IP addresses automatically. I think in the next 2-3 slides, I'm going to cover DHCP in more detail. So we're going to look at it much more at that particular point. DNS converts host names to IP addresses. Once again, I'm going to cover that in more detail. FTP, file transfer protocol. LDAP is lightweight directory protocol, basically allows different directories to sync information and things like authentication. NTP is network time protocol. This allows devices on the network to be able to get time from a server so that they're synchronized and everything else is on the same time and time zone. RDP is remote desktop access. When you want to access another server or computer on the network, you can remote desktop to that computer, and that uses port 3389 and it uses TCP. So when we're looking at the OSI, we say that on the transport layer, the two predominant protocols are TCP and UDP. So our port numbers are either TCP or UDP based on the fact that, based on whether they are connection oriented or connectionless. And that's what we covered, when we're looking at the OSI layer. And we said connection oriented, it means that TCP tracks the session and makes sure that the packets are making it to the destination, and it acknowledges that information as it traverses through. Connectionless, we say that UDP is not interested or bothered by the packet. Once it sends the packet, it doesn't follow up and track. And we say there's some applications that do well with things like UDP, but some applications don't do well with UDP and they need TCP. So when you encounter port numbers, they're going to be either TCP port 22 or UDP port 53. And some protocols are going to be both TCP and UDP. And one of the common ones is DNS. DNS is both TCP and UDP, but you'll notice that majority of them sit on either. SIP, it's a session initiation protocol. It is used with voice services. So things like voice over IP, that's going to use SIP. Telnet is when we connect, or yes, I think I've got, no, I'm not going to go there. I have a terminal emulator, but we're going to cover that later on in the series of this particular course. And SSH is a protected version of Telnet that is encrypted so that you can protect your data as it basically goes through. So these are the protocols that you will encounter. As I mentioned, it's a matter of just remembering the port numbers, and as you use more of them on a more regular basis, you are going to familiarize. But if you're not, working and using them on a daily basis, then just read your book. Many questions in the exam can come on these port numbers because you can be asked numerous questions. What's the port number for DNS? Or if I wanted to Telnet, what port number will I be going on? SSH. So just be mindful and be prepared, because there are a number of questions that can come out of the port numbers. All right, so that takes us to DHCP, which is our next protocol that we're going to discuss in more detail. DHCP, in its simplicity, is used for allocating IP addresses. There are two ways that a computer gets an IP address on the network. The first one is it can get a static IP address where you're going to hard code the address and that address doesn't change. The dilemma with that is if it's a laptop, when you connect to the wireless network and when you connect to the wired, you might have to alternate changing that static IP address. Static IP addresses are not scalable because when you allocate an IP address to one person, it means their computer owns that IP address on the network. And if someone doesn't come to work, they are still holding on to that IP address. So the other alternative is dynamic allocation of IP addresses, where you've got a pool of IP addresses and then you issue them to devices on a lease, and that lease can be 24 hours, 72 hours, 8 days. It just depends with the organization. So DHCP is the protocol that handles the process of allocating IP addresses to devices on a network. So how does DHCP function? So when a computer starts, this computer has got no IP address. It needs to talk to a DHCP server. So the first packet that that computer sends is known as a DHCP discover. So it sends a broadcast, and that broadcast is sent to every device on the network. And that broadcast will be looking for a DHCP server. So that is the DHCP discover. It's coming from the PC and says, hello, is there any DHCP server on the network? And if there's a DHCP server, it will send an offer which says, hey, I'm here. And then the computer says, oh, I got a response from a DHCP server. Now let me send a DHCP request. And in the request, it's saying, hey, Mr. DHCP, I need an IP address for me to talk on the network. The DHCP server looks at its own pool discovers that it's got free IP addresses. It then makes an offer which it sends through a DHCP acknowledgement. And in that, it provides options. And then the PC says, okay, thumbs up, I'm good. And then automatically it ends up with the 192.168.10.5 address. So I'm going to demonstrate to you what this basically looks like. Obviously, we can't do the back and forth, but I'm going to show you my lease on my computer. Right, so I'm just going to just increase the size so that it's much more clear. Okay, there we go. Right, so I'm going to type ipconfig. If you've got a PC, you can type the same thing with me, and you should be able to come up with the same results. And I'm probably going to scroll through. I've got a number of network cards on my machine, but I'm going to focus on this particular network card. Where is my pen? All right, there we go. Right, so this is my wireless network card. And I am getting a DHCP address. And this DHCP, my card is DHCP enabled. I got an IP address of 192.168.0.11. And this list was obtained on Wednesday, the 20th of September at 8:33 p.m. So I got this list yesterday. 20 September, what's the date today? No, Tuesday, sorry. Yes, I got this list today, 8:33 p.m. when my machine started. And that list is valid for 24 hours, meaning that it expires tomorrow after 24 hours. If my computer does not connect to the network, that lease is going to expire. That IP address goes back into the pool. And when another device connects to my network and it wants to use that IP address, it can be then allocated that particular IP address. Similar with our corporate environments, we have leases that get allocated by the DHCP server. Now, there's something important that I want you to note, right? Not only did I get a DHCP IP address, I also got a default gateway allocated to me by the DHCP server. And the DHCP server can also allocate DNS. So there are so many options that you can be able to configure on the DHCP server so that when someone gets an IP address, they get an IP address and also get the default gateway that's going to take them to the outside world, and also get the DNS server that you're going to be using in the organization. And all those options are provided under the DHCP scope options. So I just wanted to show you DHCP from my computer connected on the network, and I am getting a list. And right, we've got a question. Let me just put it on the screen. All right, so how does the DHCP server know that the IP address that it is going to assign to a device is not yet already assigned to another device? Okay, that's a very good question, and I'm going to try and explain it by drawing. So let's take this server. This is the DHCP server, and it's issuing out IP addresses from 192.168.10.0/24, meaning anything from 1 up to 254 is allocated. So when PC number 1 sitting here makes a request, right, goes through the whole transaction, the DHCP server allocates this PC 192.168.10.10 automatically on the list of IP addresses. .10 on the DHCP server basically gets canceled out. Right, so what it means is that I've allocated that to a PC. The next time when someone makes a query, so when computer number 2 goes to the DHCP server and asks for an IP address, the DHCP server is going to say, oh, by the way, I can't issue out 10 because 10 has already been issued. So what is the next available IP address that I have? And then it then goes to 11. If 11 is free, it issues out 11 to this computer. Another computer goes again, talks to the DHCP server, gets given .12, and then as the IP addresses get allocated, it cancels out. So that's the mechanism that it knows how to track. Because remember, it's one DHCP server that's giving out the IP addresses, so it knows in its database that if I issue out an IP address, I'm going to cancel it out on my DHCP server until the lease expires. So I lock whatever I've allocated and I give out the rest. Now, there's something that I hadn't mentioned that is known as reservation, right? So reservation is when you want to reserve certain IP addresses on your network for specific reasons. And I'll give you a typical case in point. The first one is sometimes there are devices that you want to statically assign IP addresses, and devices such as printers, right? Printers need to be static because you're pointing to that printer to print. And if an IP address of a printer changes, it means all of a sudden everyone else can print. So there are two ways that you can reserve those addresses on a network. The first one is you can not do what is known as an exclusion, right? Exclusion. And when you are defining the DHCP scope, right, you are simply saying anything from 0.0 up to 10, I want to exclude it on the list of IP addresses that are going to be allocated. So when the DHCP server issues out IP addresses, it's going to ignore anything from 0 up to 10 because you have chosen to exclude that. And it's going to issue IP addresses starting from 11 going upwards. When we look at implementation, we're going to configure a DHCP server on a Cisco device, and we're going to see this whole process in action. So that's good that you got it. So that's the first one. The second one is what is known as a reservation. Now, it's not at all times that you can statically configure IP addresses on devices. Sometimes you connect the device to the network. So let's say we connect this PC, and this PC was a special PC that we want to allocate a static IP address. So we'll connect this PC to the DHCP server. It will get a DHCP IP address, and then we then take that IP address and reserve it. And DHCP is not going to issue that IP address to anyone else except this particular computer. So there are two ways. You can either exclude or you can reserve an IP address. Now, there's a problem with DHCP. I said earlier on that DHCP uses, the first packet is a broadcast packet. I know we haven't covered this, but later on we're going to cover routers do not forward broadcast packets. So a router drops anything that is broadcast. And sometimes our DHCP servers do not sit on the same subnet with our computers, right? They're sitting on a subnet beyond a router. And when this packet gets sent, it gets to the router says, broadcast, I'm going to drop you. And our packet won't make it to the DHCP server that is sitting on the other side of the network. So in order to curb that, there is something known as DHCP relay. This is where you tell this router that my DHCP is not located on my subnet, but it's located on the other side of the router. And when the router sees this DHCP relay, what it then does is that it takes that broadcast packet, converts it into a unicast, and then it sends the unicast to the DHCP server, and it starts relaying and talking to the DHCP server on your behalf, and it gets the list coming through. And the reason I'm mentioning this is because it's in the textbook. It can come in the exam. They might ask you what DHCP relay is and how it works. This is basically what DHCP relay is, and that's how it basically functions. So that is DHCP server. We are going to go through the configuration later on in the course. So we'll then cover how we'll configure this. I might just add configuring a DHCP scope on a Windows server. I know it's not in the context of the exam, but the focus is practical knowledge, right? So we will need to cover this so that you can be comfortable in being able to then create your own DHCP server and see it allocating IP addresses on the network. So the next one is the DNS, domain name system. I'm sure many of us on a daily basis go to websites, www.comptia.org, netflix.com, facebook.com, youtube.com. Computers don't talk in URL terms, right? A computer does not understand what comptia.org is. So we need something that translates this user-friendly name that you and I type. Just a second. Right, we need something that translates this user-friendly name into the IP address that a computer understands. And DNS is the system that does the translation. So a DNS server, in its simple terms, translates between the friendly domain name onto the IP address, which is at the back end, because servers across the internet talk in IP addresses. So you can think of DNS as a phone book. I know nowadays we don't need yellow pages or phone books, but once upon a time, there was a time when phone books was all that you had. If you wanted the mechanic, you'd go to the yellow pages, look for the mechanic, get the phone number, call the mechanic, and then get the help. The phone book allowed you to convert the user-friendly name. So you look for a section for mechanics, and then you get the phone number, and then you can call. Similarly, DNS, friendly name to the IP address. And as I always want to do. I always like demonstrating so that you can see. And if you've got a computer, I'm assuming you've got one, you can follow with me and we can be able to look. All right, I'm just going to try and clear my screen. Let's erase this. All right. CLS. All right, so let us ping, not ping, let's do an NS lookup. Right, so NS lookup is what is the IP address of a particular website. And in this case, we're going to go youtube.com because we're watching this on YouTube. So let's press enter. And the IP address for YouTube from my computer is 142.250.67.14. That might not be the same for you. Remember earlier on, we mentioned about the Anycast. And I said Anycast is 1 to nearest. So if you are sitting in the US, when you do the same thing, you get a different IP address. And the reason why you're getting a different IP address is because your nearest Anycast address is going to be different to mine. But I want you to see something on the screen. So the first thing that came up was the IP address of this friendly domain name. So youtube.com converted into IP address is 142.250.67.14, according to me. Now there is this non-authoritative answer. So there is a DNS server that translated this information for us. And in my case, it was my home router, right? This was acting as the DNS server, and it was not the authoritative server to the youtube.com record. And I'm going to go into detail explaining authoritative server and what that basically means. I just wanted to show you. So let us look at another example before we go back to our slide. And I'm going to erase this. And so the next one is we're going to do an NS lookup. This time around, we're going to use facebook.com. But instead of querying my local DNS server, I want to query the common public DNS server of 4.2.2.2. So when you're doing an NS lookup, you can ask your machine, your local server, you can query your local DNS rather, or you can query a DNS server that is sitting on the internet. So I'm going to press enter and it returned. So once again, this is the DNS that basically did the query for me, right? So I queried that DNS server and then it came back to me. It gave me the IP address for Facebook. Now, this is the IPv6 address for Facebook. This is the IPv4. And I've got that particular IP address. So DNS server basically takes the friendly www.facebook.com. You send that to the DNS server, and then it spits out 157.240.7.35. That's how a DNS server functions. Now, there are things that happen behind the scenes. As you can imagine, these records change on a regular basis, right? Today, Facebook might use this IP address. Tomorrow, it might use a totally different IP address. Or you and I can register our own website, right? So let's say, for example, we start our networking company and we're going to call this ABC Networking.com. And you've got a website. Behind this, there is an IP address, right? Maybe we're using 5.5.5.5.5. That's our hosting company. This record has to be propagated across the entire world so that someone who is sitting in Brazil can be able to go to our website and find the services that we offer. So there are multiple DNS servers that are available on the internet. And DNS servers are structured in a hierarchical format. Yes, DNS servers are structured in a hierarchical format, meaning there is the root, there is the top level, there is the second level, and then you got the subdomain. And what do I mean by root, top level, and subdomain? Let me just return to our slide. So the top part of the highest point of the DNS hierarchy is known as the root, right? Root is represented by a dot. And this dot is not, we don't include it in when we write a fully qualified domain name. And what do I mean? We type www.facebook.com, but after .com, there is a dot that is there. We don't type it, but this dot is known as the root. This is the starting point of our DNS resolution. And there are servers that are known as root servers. These are the ones that host the dot. And then after that, we've got the .com. And .com is known as the top level domain, right? So we've got .com, we have .mil, which is military, .edu, .org. These are top level domains. And then after that, we then have the second level domain, which is the name of our domain. In our case, Facebook, Twitter, that is the second level domain. And then sometimes we have subdomains, which might be the geographical location of some of these entities. So in our case, let's take, for example, India.ebay.com. And then we've got this dot, right? So this dot signifies the root. .com is the top level domain. eBay is the second top level domain. And then India is the subdomain. This is the hierarchy that DNS uses to maintain records. So when you make a query, you start with the root, and depending with the .com or .edu or .military, you get sent to the different respective DNS servers that are authoritative to that particular top level domain. So if you're looking at a .edu, right? So you're looking at Harvard.edu, you query and you first hit the top level, so the root then sends you to the .edu. Under the .edu, that's when you're going to find DNS servers that are authoritative to the .edu top level domain. If you're looking for .com, you get sent to the .com, and in here you're going to find DNS servers that are also there to service the .com top level domain. So that's just the structure of DNS. So what records do we find with DNS? There are quite a number of records, but the ones that are important for Network Plus is what is known as an A record, right? An A record is a record that maps a host name to an IPv4 address. So we looked at facebook.com, and we said the IP address is 157.8.5.24. When this record is recorded in the DNS server, it is known as an A record. So when you query the DNS server and you say you're looking for facebook.com, it goes through its database looking for an A record for facebook.com. It finds the A record and says, oh, what is the IP address? Oh, the IP address is 157.8.5.24. Then it returns that information. And then your computer then takes that IP address and then starts routing packets in that direction, because now it has an IP address that it can use. So the first one is an A record. The second one is what is known as a CNAME record or canonical. And the CNAME record is basically an alias for an existing record mapping to the same IP. So sometimes you might want to have two different names pointing to the same destination, right? So let's take this example, facebook.com. Maybe I want to point eu.facebook.com to the same IP address. So I'm going to create a CNAME record, right? So this will be a CNAME record that will be stored in the DNS. And when I query the CNAME record, I get pointed to the eu.facebook. The IP address is still the same with facebook.com, but I'm using a different record pointing to the same IP address. So that is that record. The other one is known as an MX record. And this is important for mail servers because it maps a domain name to an email server for that particular domain. So when you're sending email, you got gmail.com. Gmail.com will have an MX record, and that MX record is propagated across the world. So when you're sending emails and you want to find the gmail.com email server, you use the MX records to take you there. So MX records are mainly reserved for Exchange servers. And then the last one is a pointer record. And a pointer record is basically used for reverse lookups. And I'm going to do a reverse lookup so that we can be able to see how a reverse lookup functions. And I'm going to try and bring back my command line. So earlier on, we did a forward lookup, right? Forward lookup was NS lookup, and we're looking for google.com, and we got the IP address. When you do a reverse lookup, you're putting the IP address and you're trying to find the host name. So let's do an NS lookup for, what was the Facebook IP address earlier on? It was 157.240.7.35. So when you press enter, the reverse gave us edge star mini.shv.sin6.facebook.com. When we did a forward lookup, we got the tidied up version of facebook.com. But when you did a reverse lookup, now we're getting the actual server that we're hitting when we are doing the query. And pointers are very important for security reasons. Sometimes when you want to validate the authenticity of a domain, when you do a reverse lookup and you're able to get a record, a pointer record, that kind of validates. I'm not saying all the times it's going to be genuine, but genuine unmasked domains tend to have a reverse lookup address so that you can then do it in reverse. So you can play around, let's do one more in the famous 8.8.8.8.8.8. Let's see where that brings us back to. So let's do a reverse lookup, and that is the DNS for Google. So that's the Google DNS server. And the other popular one is 1.1.1.1, which is Cloudflare. And that takes you to 1.1.1.1, which is the Cloudflare DNS server. So multiple DNS servers across the internet. And these are the records that you find when you are dealing with DNS servers. So let's go back to our slide. So because there are multiple DNS servers across the world, and the records that they keep are known as zones. And DNS servers need to communicate so that they can update each other. And that updating between primary and secondary DNS servers is known as a zone transfer. This is when they are synchronizing the two. So a zone transfer is basically synchronization of DNS servers. If you've ever registered a domain, you know that when you register a domain, they'll tell you that check in 48 hours, it would have propagated across the world. What they're basically meaning is that in 48 hours, that record would have, the DNS servers would have done a zone transfer to the extent that that domain name is now resolvable from any DNS server across the world. Then there is what is known as the DNS time to live. And this is the amount of time that the DNS server caches information. So when you query a public DNS, your local DNS server is going to cache that information for a certain period of time, so that when you make further queries, instead of it going to the public DNS servers again to retrieve information and come back, it's going to take a lot of time. So it's going to keep it closer, right? Just think about it. When you're watching a movie, you take your popcorn, you take your juice, and you sit on the couch. The reason why you do that is for comfort, right? If you want to eat something, the popcorn is next to you, the juice is next to you. That is your cache, because that is closer to you. But when the popcorn runs out or the juice runs out, you're forced to go to the fridge. And that is an inconvenience. Same thing with DNS. It caches that information and keeps it closer, but it doesn't cache it forever. It's got a time to live. So the time to live is the amount of time that it holds that information before it expires. When it expires, it has to go back and then query the public DNS servers to get further information. Forward lookup is when you resolve the name to the IP address. So when you're resolving google.com to the IP address, that's a forward lookup. A reverse lookup is when you are reversing the IP address to the host name. That is a reverse lookup. And then a recursive query is when you query a DNS server, but you ask it to answer you. And if it doesn't have an answer, it comes back and says, I don't know, versus asking the DNS server to go and query other DNS servers to come back with the answer that you're looking for. So when you do a recursive query, you are saying, I want the answer from you, but don't refer me to other DNS servers. If you don't have an answer, that's fine. An iterative query is the one that you are allowing your DNS server to query other DNS servers. So let me draw this so that it's probably clear. So we've got your PC sitting here. You want to go to google.com. I hope this is visible. Google.com. So you query your DNS server sitting here. When you do a recursive query, what you're simply saying is, give me the answer, but don't ask any other DNS servers, either on the network or on the internet. I want the answer from you. But when you do an iterative query, you're simply saying, in the event that you don't have the answer, you can go ahead and ask other DNS servers to then come back and give you feedback. So that's the difference between an iterative and a recursive query when you're dealing with DNS. So that basically wraps up. There is a lot on DNS, but for the purposes of Network Plus, this is just what we cover. There's things like startup authority, which you haven't covered, which you probably need to go and look into to be able to then learn and understand. Now we get to the exciting part, NTP, Network Time Protocol. Time is very important on a network, and it is important for two reasons. There is something known as syslogs, right? Syslogs are basically, logging interaction that happens on a network. And when you collect logs, timestamps are very important. So if anything happened in the network at work, that the syslog server captures the event and captures the time. When I get into the office tomorrow morning, I can look at the logs and I can be able to know that, oh, by the way, last night at 10 p.m., one of our routers lost its BGP peers and it regained the neighborship, but I can investigate why it went down. And if I don't have the right time, it means that my troubleshooting is going to be impeded. Network devices, when they have local time is not the most reliable. Devices lose time, and sometimes with local time, it is not synced correctly. So one router might have a different time, and that makes collation of logs a bit of a challenge. So an NTP server provides you with a central time server that all your devices on the network can be able to query. So all your routers and your switches will then talk to the NTP server, and then they'll get their time from there. Very important. 3 things that you need to know about an NTP server. A client is the device that's requesting the time from the NTP server. So in our case, our router will be a client, our switch will be a client. Servers can also be clients. And then the server is the node that is providing the time. So this would be our NTP server, and these would be the NTP clients. Now, the third element with NTP is something known as stratum. And stratum basically means the number of hops between you and the source of truth. And the source of truth, in as much as time is concerned, is something known as atomic clocks. These are considered the accurate time machines. And you've got a few of them, spread across the world. These are the source of truth in as much as time is concerned. I'm sure you've heard about the fact that most watches lose their time over a period of time, right? Your clock is not as accurate, but these atomic clocks are the source of truth, and they're known as stratum 0. So when you talk about stratum 0, we are simply saying you are at the source of truth in as much as time is concerned. And then you've got devices that talk to the stratum servers, so to the stratum 0 or atomic clock servers to get their time. Those devices are known as stratum 1 devices. So when you see the stratum value, it's basically just saying how far are you from the source of truth. So if your devices are connecting to a stratum 2 device, it basically just means that it has to talk to a level 1 and a level 1 talks to a level 0 in order to get the time. And the further you go from the source of truth, the more the time synchronization kind of differs milliseconds as you move further. And I think the limit is stratum 15. Network devices don't trust anything that's more than 15 hops from the source of truth because it's considered too far. So when you're configuring Cisco devices, mainly you will need to configure this stratum value, and that's why it's very important for you to be able to understand. NTP operates on UDP and is UDP port 123. So if you're analyzing your network traffic, either using NetFlow or on a firewall, and you come across port 123 and you're wondering what that traffic is, that is basically NTP traffic. So if you've got an opportunity to analyze firewalls, have a look and you'll be able to see the traffic basically flowing through. There isn't much to NTP other than the 3 aspects that we've basically covered. So now we are gravitating out of network protocols, out of the OSI and the IP addressing, and we're starting to get into your data center architecture. I think I mentioned something earlier on when we looked at OSI. I spoke about the 3-tiered system. In this topic, we are going to cover the different data center architectures, why we need such architectures and what purpose they serve. And that will be taking us preparing us to the next section that we're going to cover in the course. Remember, the first section focused on network fundamentals. So just dumping a lot of information about protocols, about how DNS works. In the next section, it's network implementation. This is where we now get into the exciting part, the configuration, understanding, VLANs, routing protocols, all the fun stuff in networking is going to be in the next section. And I think that we'll cover in the class on Thursday. And next week, we're going to be looking at network implementation. So you don't want to miss that particular class. I will post the class link after this particular class. So let's go back to data center architecture. What is covered and what is it that you want to know? So the most common tier system in networks is known as the three-tiered network. And what the three-tiered network, it was comprised of the access layer, the distribution layer, and the core layer. On the access layer, this is where you find the access switches. And the reason why they're called access switches is because this is the switches where the end users connect to that particular network. So you'll have multiple ports and different endpoints connecting to the network via the access layer. On the access layer, this is where you also find wireless access points. All right, so your Cisco APs connect at the access layer. So you find end users, layer 2 switches are operated at the access layer, access ports. Spanning tree is an access layer protocol. VLANs operate on the access layer. Power over Ethernet, they are all functions of the access layer. So when you're thinking about the access layer, just focus on the devices that provide end user connectivity. So when you're in the office and you're connecting to the network, there's a 99% chance that you're connected onto the access layer because that is the bottom layer of the network. And then that is followed by the distribution layer. And the distribution layer basically is used to aggregate the different switches that are on the access layer and connect them for high redundancy. So on a typical network, let me just erase this and I'll probably draw this. So these will be your access layer switches. So we're probably going to draw 3. And then you'll have 2 distribution layer switches that will be connected to each other for redundancy. And every switch is going to have 2 links to either of the 2 switches for redundancy. This is switch number 1, this is switch number 2. In the event that this switch goes down, traffic can still flow via this switch to go to the rest of the network. So the distribution layer is there for aggregation of your access layer switches, but it also provides redundancy. And later on, we're going to be looking at the different protocols that enable for that redundancy at the distribution layer. So the devices that you encounter on the distribution layer are routers. Routers are layer 3 devices, multi-layer switches, firewalls. They operate on the distribution layer. And then the top tier is the core layer of the network. This is the core or the brains of the network. And this is where packets get forwarded. This is where aggregation of the bigger part of the network is concerned. And most of the times you'll have 2 core switches and they connect. So the reason why the core layer is there is that the distribution layer connects to the access layer switches, which slow down the processing of information. And you don't want your core sitting closer to the access layer. So depending with the size of the organization, you would implement this 3-tiered system. Most organizations use the collapsed core, which is they eliminate the core part of the network and they combine the core and the distribution and make it one network. So that's basically the 3-tiered system. It's been popular for quite a while, but there's a shift from the 3-tiered system to what is known as the spine and leaf. And this is more focused towards data center, and as you go towards software-defined networking. And what spine and leaf is, basically, you have your main switches on your network, which are known as the spine switches, and then you got the leaf that are acting as end nodes. They're not dumb terminals, but they're not super intelligent, and they're just providing endpoint connectivity, and they connect to the spine to be able to then get reach on the rest of the network. And these switches are dependent on the spine for everything that they basically require. So it's like a leaf. The spine of the leaf is the most important part. It's the one that feeds the nutrients, is the one that feeds the water to the rest of the leaf. So the leaf is only as good as the source of the nutrients, which is the spine. Same thing with human beings. The spinal cord is the core. The reason I'm moving my hands is because the spinal cord has carried that information. If something happened to my spine, the top part of my body might not be able to function. So it's a similar concept when you're dealing with devices on the network. Now, this has been the buzzword, software-defined networking. Everyone is talking about software-defined networking. And what is it? What is it that you want to know? What is it that you're supposed to know in as much as software-defined networking with Network Plus? So for us to understand software-defined networking, we need to work out what was the problem before SDN basically came into play, or as it's coming into play. For most people that have dealt with network devices, the challenge with network devices is that when you're managing network devices, devices are managed individually. So if you got 10 switches or 10 routers per se, or switches, right? If I want to make configuration changes, I have to connect to these switches individually to make the changes on the network. Now, this does not seem tedious because, 7 switches, sure, I can get a cable, plug in to 7 devices without much of an issue. But imagine a network with 300 devices. That then becomes a nightmare because I have to connect to 300 devices to make changes. And depending on what I'm changing, let's say, for example, we want to change the passwords on all the switches and all the routers. I have to connect to 300 devices individually to be able to make that change. And next month, when we change the password to something else, the same process happens again. And the reason why this was taking place is because the control plane and the management plane was all on the same device. So the control plane, management plane, and the data plane. So the control plane is basically what controls the configuration of that particular device. The data plane is focused with the transmitting of data as it flows through the particular device. And the management plane is focused on managing that particular device, so changing configurations. So all these things were contained on the device. And for that reason, you needed to manually connect to devices individually. Now, there are softwares such as Cisco Prime that simplified that whole process and allowed you to, at least manage multiple devices at the same time, send one command that goes to multiple devices, but still, you are still dealing with that one-to-one. So with software-defined networking, the objective was to break up these planes and take them away from the actual physical device and abstract them in a software environment or virtual environment so that the controls are not, the control plane is no longer located in the same place as the actual physical device. So when you then take the control plane out of the device, it means that you can then multiply manage different devices, because then the control plane is centralized. And this is typical of Cisco wireless controllers and access points. So with wireless networks on Cisco, you've got the controller known as the WLC, and this is basically the brains of the whole wireless network. And then you've got access points that connect to the controller, and they basically listen to the controller and get all the information from the particular controller. So they are more like dumb terminals that basically come on the network, ask the controller what it is that they need to do, and the controller then allocates accordingly. And that is what software-defined networking is basically trying to bring to the network, to the network layer. So the four most common layers that you find with SDN is the application layer, and this is where you've got the APIs of the software that basically controls the entire network. And then we've got the control layer, which is basically the single pane of glass, which allows you to see everything that's happening on the network, and basically is the brains. You've got the infrastructure layer, which is the hardware, and then you've got the endpoint devices. So your actual switches would basically fall in the infrastructure layer. And then you've got the management layer, which is basically dealing with the management of those devices. So when you can decouple all these layers from the actual device, it means that you have the ability to then control them from a central point, and then also you're then able to have a single point of view or perspective as to what's happening throughout the entire network. So whenever you hear about software-defined networking, the whole objective is basically abstracting or decoupling all this to a more software model, which then makes it easier for you to then control or configure the network devices all in one go. The one thing that you need to know, two words that get thrown out when you're dealing with software-defined networking is northbound or southbound traffic. And what they basically mean by northbound traffic is any traffic that's coming from the infrastructure layer trying to talk to the API or to DNAC, being the system that controls Cisco devices on a software-defined networking. Any traffic going up is northbound. And then when you're pushing commands from the application layer to the physical device, that traffic is southbound, right? So it's coming from the application layer going to the device, southbound, coming from the device going to the application layer, that is northbound traffic. And then you'll find east-west. East-west is just basically traffic that's flowing on the network sideways from one switch to another, from leaf to leaf, instead of leaf to spine, right? Leaf to spine would be northbound. Leaf to leaf will probably be east to west. So those terms are going to get thrown around, and that's what those terms basically mean. All right, I don't know if there's any questions. If anyone's got any question, anything that need me to clarify, please don't hesitate to ask. I always say ask questions. It will help someone else who might be scared to ask, but not sure about a particular concept, to also then get the benefit of what it is that is basically being covered. But if you've got no questions, then we can be able to then proceed. All right, so this is basically going to be our last topic for the night. And which brings the end of the first section of the course, which is the network fundamentals. And the next lesson, we're going to be looking at the nicer, interesting part, which is the configuration and cloud concepts. I mean, cloud is the buzzword. If you want to find a job in IT, if you're not working in IT, if you talk to people, they'll tell you you need cloud, cloud knowledge, cloud infrastructure. But what is the cloud? Is there some magical cloud where all the infrastructure sits? Or what is deemed, cloud? And we'll cover the different models that you find for cloud architecture. And the first one is known as a private cloud. In simple terms, cloud is basically servers that are sitting behind the scenes, right? So behind whatever cloud is basically servers that are sitting behind. These servers could either be sitting in your private data center, and thus it's called a private cloud, right? So they're sitting in your own private data center. No one else has got access to them other than yourselves. This is typical of government departments. They don't want, for security reasons, for data to be sitting on public cloud infrastructure where they don't have control over it. So they will then create their own data centers, and then they will have different offices communicating with those data centers. So that then becomes your private cloud. It is owned by you, no one else has access to it. The second model is public cloud. This is when you outsource this to the two most common cloud providers, AWS and Azure. And there's also Google, which is also in the cloud space. So you hand over, they control the infrastructure, they control the security in and out of the data center, they control the hardware. You basically utilize their services and they host that particular information. And whilst that is scalable and it is fantastic, it also comes with its own disadvantages and challenges. I'm sure you probably heard about the Uber hack that took place about a week and a half, depending on when you're watching this video, when it was recorded or when it's being recorded right now, about a week before Uber got hacked. And one of the hacks was due to someone gaining access to their cloud platform. And thus, they managed to then get the data out of that. So there are challenges with public cloud infrastructure. It might be scalable, might be cheaper, but then from a privacy standpoint, you don't have much control. And then the third one is a hybrid. And this is basically a mixture between your private cloud and some infrastructure that is sitting in either AWS or Azure. So these are the deployment models that you can be able to implement when you go into the cloud, right? You can either have your own private, or you can either go and have a go fully public, or you can have a hybrid between the two. So in the cloud, there are deployment models, there are also service models. And I'm sure you probably heard about some of these acronyms, IaaS or SaaS, as they call it, which is software as a service. IaaS is infrastructure as a service. And then PaaS is platform as a service. What are these? What do they do? What difference does it make? Infrastructure as a service is when you rent virtual servers that are hosted by a provider. So if you've been to a data center before, you have what is known as racks. So a data center is basically mainly made up of, racks, and in these racks, you have server infrastructure, going all the way. So infrastructure as a service, you are renting virtual servers that are hosted by the provider. So they own the servers that are connected in the data center. You are renting the abstracted virtual environment. So you don't control the underlying server infrastructure. They do the maintenance, and if the server infrastructure is redundant in terms of it has grown old, they replace it. It's not your problem. So that is infrastructure as a service. You are renting the virtual servers. Software as a service, you don't own anything. You're not renting the servers, you are renting or paying a subscription for the application that you're using, but you're not involved in any of the underlying details such as infrastructure of that particular application. And typical cases in point is Gmail, Outlook. You and I have an email address, Gmail. We don't know where the servers sit. We're not bothered about the servers and the maintenance of the servers. All we need is email working, but someone else handles the underlining. And if you're looking at it from a corporate environment, you're looking at things like Office 365. That's a typical case in point of a software as a service. And then platform as a service, this you'll find in cloud providers like AWS. They have what they call Lambda. Lambda is a serverless system that allows you to run processor and memory intensive code so that you can then be able to get different permutations and results. So platform as a service is when you go to AWS and you use their platform to do the things that you want to do, run different sequences on data. When you're done, you stop that process from running and everything else goes back to normal. So platform as a service, you just basically go in there to run infrastructure or run code on the platform that belongs to the cloud party. So these are the three service models that you're likely going to encounter when you're dealing with service providers. When you go to them and say, hey, I want to use your service, they're probably going to ask you, what is it that you want? Do you want infrastructure as a service? You want software as a service, or platform as a service? And now we're going to close off with the three cloud concepts that you're going to find whenever you talk this cloud language. These terms are going to throw around, or they're going to be thrown around, and you might wonder what it is that they mean and what it is that they do. And the first one is elasticity. And elasticity, just like an elastic, elasticity is basically the capacity of your server infrastructure to be able to shrink and grow on demand. And the best scenario that I can give is Christmas. I know we're a couple of months away from Christmas, but during Christmas, most people, or maybe Black Friday, and Black Friday will probably fit the bill in a much more easier way. So Black Friday is that one day of the year when there are specials and everyone else takes out their credit card and then they go and buy stuff. Now, the demands of platforms such as Amazon and eBay on Black Friday is probably going to be 10 times the normal demand of those services on a normal daily basis. So with elasticity, the cloud infrastructure will have the capacity to be able to grow as demand for the services is required. And then when demand is no longer required, the infrastructure shrinks automatically. And that's the concept of elasticity. The second one is infrastructure as code. And infrastructure as code is the transformation of networks being built using code. And I know it might not seem like it might not seem to make much sense, but I'll try and explain it. So the predominant network has been physical, right? You got a physical router, you got a physical switch, you plug in the network cable, and everything else basically functions. But with the advent of virtualization, all these physical devices are being abstracted into virtual devices. Remember earlier on in the course, we looked at virtual routers and virtual switches, virtual network adapters. And in most cloud environments, networks are basically architected using code. So you can run network code, and that code basically creates an entire network, all the way from a load balancer to a default gateway to the server that sits underlining, and that is basically running as code. That's what infrastructure as code is. It's basically virtualized networks that are maintained using scripts. And when you look at JSON in AWS, you can basically write a script of your entire network, and when you run it, it basically builds up a network in about 5 minutes, something that would have taken longer when you're dealing with physical infrastructure. And the last one is multi-tenancy. And as we alluded to earlier on, when you're running in the cloud, you are sharing infrastructure. And it is very possible that McDonald's and Burger King, which are competitors in real life, might have their servers sitting on the same VM host because they are hosted in AWS, unless otherwise they've made prior arrangements to be able to then make that segmentation. But multi-tenancy basically means that the amount of multiple tenants that are available in the cloud, and that is basically shared. So you probably share your infrastructure. I thought I had questions somewhere. Oh man, I think I probably didn't put the slide. Anyway, so yeah, that was a bit of a mouthful. And that basically closes off the network fundamentals part of the course. On Thursday, we are now going to go into network implementation. And for me, that's my favorite part. Fundamentals are good, but I like, getting my hands dirty and getting the configuration. And I'm sure many of you, that's what you're waiting for, getting to the part where we can start breaking things, see how things work, and see how things function. And that's what we're going to be looking at on Thursday. I don't know if there are any questions. I'm probably going to, give about a minute if there's anyone with any questions. I wanted to do a quiz. So whilst I'm waiting for anyone who's got any questions, I'm just going to try and see if I can quickly pull out the slide that I made that has questions. And I'm probably just going to pull it out as is. Just a second. Okay, it's just taking a bit of time, but I think I managed to find it. I'll just try and see how best I can bring it onto the screen. All right. I'll just bring this section on the screen. Let's just zoom this. Okay. I'm not so sure. Let me do this. Let me just take this here. Just make sure that I've got that, and then let me just try and see if I can see. Oh, there we go. Not as much. Okay, so I'm just going to take this here. I just want to make sure that I can see the screen that I'm sharing. Okay. All right. All right. Yeah. So the first question, how many bits is an IPv4 address? This is probably going to be quicker. Sorry, I've got a question. Are video game servers private or public clouds? That's an interesting one. There is no definitive way of being able to tell whether the video game servers are public or private cloud. However, I'm going to be leaning towards public cloud, and I'll tell you the reason why I would lean towards that. Most video games, the objective is to have an environment where demand that happens with a game, you have the capacity to be able to provide for that particular demand. And that is likely going to be found in public cloud infrastructure because of the scalability or the elasticity of the cloud environment. So when you launch Grand Auto Theft, and there's another hack that happened on that one, but anyway, when you launch, let's say, a new game, today there might be 10,000 users that are playing it. Tomorrow there might be 1 million users that are playing it. And you want a cloud environment that allows for elasticity. Private cloud is usually retained for organizations that are sensitive about privacy and they want to protect their data. And government departments, banks, credit card organizations, these are organizations that tend to store their data in private cloud infrastructure where they control everything and they can be able to secure people who go in and go out into that particular data center. The other reason why you got private clouds is there is some sensitive data that is country specific, right? So different governments prohibit their data to be carried or stored anywhere outside of the country. So in order for you to control that, because with public cloud, you don't control where the data sits. They might have a presence in Australia, but they might be storing their data in Singapore. And that then becomes a breach of government departments. So whenever you deal with government departments and data and data storage, the location of the data center then becomes more pivotal. So video game servers, I would say they would lean towards public versus private because they've got no benefit going into a private cloud infrastructure because they're not trying to protect much data. So that would be my take on that. But there's no 100% guarantee. It's not like public cloud servers have got their own IP addresses that are different to public. They run the same IP addresses, so you can't tell whether it's a private cloud or public cloud based on the IP address. All right, so back to our quiz. The first one, an IP address has 32 bits. Right, so 32 bits is the answer for the first one. The second question, what are the two protocols that operate at the transport layer? We spoke about it earlier on. We said TCP and UDP are the two predominant protocols that operate at the transport layer. You also have ICMP. It operates at the same layer. What does CAN, MAN, and SAN stand for? So CAN is a campus area network. MAN is a metropolitan area network, and SAN is a storage area network, which is basically a network of storage devices. Question number 4, what is a VNIC? What is a VNIC? A VNIC is basically a virtual network card. That's a virtual network interface card. And these are found in virtualized environments. We said that there's a host, and inside the host, you got multiple VMs, and those VMs will have virtual network cards, which allow them to talk to a virtual switch, which then talks to the external network to then take the traffic to flow outside. We spoke about UTP. What is the maximum distance for a UTP cable? And I said the last time UTP has a limitation of 100 meters before attenuation or degradation of signal starts kicking in, and it affects the ability of that UTP cable. Question number 6, can you convert this IP address to binary? Can you convert this IP address to binary? I'm probably just going to erase that 192.168.20.54. So once again, just write 128.64.32.16.8.4.2 and 1. And 192 is going to be 1100000, and 168 is going to be 1010100. Right, it's basically 128 plus 32 is 160 plus 8, 168. Right, so we've got that. And then 20 is going to be 0001010. And then 54 is going to be 0011. That's 48. 48 plus 8 is 54. So that's the equivalent of that IP address in binary. What is the range of a class A address? We said there are 3 classes, class A, class B, and class C. And a class A address is basically anything that starts from 1 up to 126. Class B is anything that starts from 128 up to 191. And then a class B is anything that starts from 192 up to 224. So the range of a class A address is any IP address that starts between 1 and 126. And then what is the port number for NTP? We said the port number for NTP is 123. And it's UDP. UDP 123. And then the last 2 questions is, what is SaaS? We said SaaS is software as a service. This is when you don't own any of the infrastructure. You just pay a subscription and you access the software. So services like Dropbox, Office 365, Salesforce, all these are applications as a service. You don't own it, you pay a subscription, and you use the particular application. And the last one is, which layer of the OSI uses MAC addresses? We said the OSI is made out of 7 layers, and MAC addresses operate on the data link or layer 2. So MAC addresses operate on the data link layer of the OSI, and this is where you come across MAC addresses. So I hope the quiz was easy, and you could answer these questions without any issues. If you struggled, then maybe you might want to watch some of the videos. If not, you can, get in touch with me and ask any questions that you might have. So yes, that's it for today, guys. That brings us to the end of phase 1 of this bootcamp. And on Thursday, we're going to be starting on phase 2. Once again, if you've got any questions, my email address is going to be somewhere in the description. Don't hesitate to send me an email, or you can send your questions live and I can be able to respond. And don't limit this to the course in question. Anything related to networking, just shoot through. I'll answer where I can answer and be able to, help you as you go along the way. So that's it for today. Thank you. Thank you for watching, and I will see you in the next one.